video on vector fields. So this is a fairly new topic, I believe, once at this stage. When I took this class before and we started going over vector fields, I'd never really had experience with them. So anyways, so what a vector field is, it looks somewhat like, I'm just drawing it in the first quadrant just for convenience, and they could be anywhere really. But basically what you have are points and then vectors attached to them. Okay, and they can go in any direction. It depends on the function or the vector field. I'm just drawing them all like that, but they could go up, they could go sideways. It just depends on the function that you're given. So this is a weird vector field, admittedly, but what a vector field is the following. So a vector field F, capital F, they usually use F for some reason. So what it does, it assigns to each point, and we'll call the point P, just because P corresponds to point, a vector, and the notation is F of P. So you plug in the point, and this is the vector that you get at that point. Okay? So this represents, it could represent something like, and I think the book gives you an example like, oh, the velocity of wind at that point or something. So that's what I'm going to write here, just as an example. Something like velocity of wind at the given point, or at any given point, I'll say. Okay, and then also another, we're just starting with definitions here so you can get the concept. So domain of F, the vector field, is the set of all points P, for which F, the vector field of P, is defined. Okay? Alright, so those are some important definitions here. So this is what a vector field is. Vector field F in this case. And they can be called anything really. You could be given a vector field G, or a vector field, I don't know, U, or something like that. Anything like that. And then this is your domain. And so basically what we're going to have is, well, I'll give a more concrete example on the next slide. So let's say we're in the R2. So in R2, which is like a plane, right? Two-dimensional plane. So let's say we're in the XY plane. Okay? And let's say, so what we'll have, our vector field is going to look like some f of x comma y, because we're in two dimensions. And this is going to equal a vector. But this vector is going to have, okay, so it's going to have two components since we're in two dimensions, right? So this just means 2D, okay, so a flat like plane or a paper. And then what we're going to have for our two components are some other functions as well. So an f sub 1 of x and y, and an f sub 2 of x and y. Okay, so basically what we have are these two components in here. So each component of the vector depends on the point P, or yeah, we could call this P. This is like a point with two coordinates, x, y. Okay, each point P equals x comma y. Alright, so let's say, for example, I'll just do a little quick example here. So let's say our point is 1, 1. Well, actually this will be round brackets here. Round brackets. Okay, those are some weird round brackets. Hold on, let me start over. So P equals 1, 1. Alright, so this is our x and that's our y, like normal coordinates, right? And let's say our given vector field is f of x comma y equals y minus x comma x. So in a problem, they'll give you the vector field. They'll give you the vector field, and then they'll tell you like to plug in a point or find the vector at that point or something like that. So what I'm going to do is we're going to find vector associated with point P. Okay, so this is point P, all right, and basically what we're going to do is just plug those in. Simple enough, right? So f of the point 1, 1 is going to equal, or we don't need the brackets there. Anyways, so y minus x is 1 minus 1, comma 1. Right, so this is going to turn out to be 0, 1. And what that means is that when you have, usually what 0, 1 would look like as a vector is going to be something like, here's 1 and here's 1. So 0, 1. So the vector 0, 1 would be 0 in the x direction and 1 up. Okay, so that would be the vector. However, now in the vector field, this is what we're going to have. It's a little bit different. So what we have is 1, 2, 1, 2. So now we have this vector, because that's what we got from plugging it into the vector field formula or equation. But now the base of it, so where we start, is not at the origin, not necessarily at the origin, but at our point P. So where's our point P? It's at 1, 1, so 1, 1. So here's the base of it, and then we just have to move this guy up to that point. So then we just do 0, 1, starting from point P. Okay? So that would be the vector attached or associated with point P. All right? And then also, additionally, when we move into R3, which we will, so R3 is a three-dimensional space, so 3D, and this is, I'll just say it's like X, Y, Z space. Okay? So we have 3 axes now, 3 coordinates. So what this is going to look like is you're going to have an f of x, comma, y, comma, z. And now, I actually might need more space, but we'll try to squish it in. We have 3 components, okay, and each of them depend on x, y, and z. Okay, x, y, and or z. Sometimes you'll have a vector field which, like, when the components, like, let's say be just a y or something, and then obviously you don't have an x and a z there, but basically the whole idea behind this is that the components that make up the vector, they depend on some combination of x, y, and z. Okay? Alright, so now let's do another quick example of associating a vector with a point. So let's see, we have our example, and this is going to be, it's going to ask which vector is attached, or associated, either way, attached to P equals 1, 2, 4. So here we have a three-dimensional vector. Okay, so with, and then I'm going to give you the vector field, that'll be z plus 2x, comma, y squared, comma, x, y. Okay? So basically all we have to do is plug in P for all of these. So x equals 1, y equals 2, and z equals 4 from our point. And then if we plug this into our vector field, like that, we're going to get z plus 2x. So that would be 4 plus 2 times 1, and then comma y squared, so that's 2 squared, and then x times y, which is 1 times 2. Okay? And then we just evaluate, and we get 6, 4, 2. Alright? So this would be the point there. And this is the vector based at P, so that would equal 1, 2, 4. So that's how you would draw it on a three-dimensional graph. Okay? So now on to something a little bit different but still related. So now I'm just going to go over, sometimes you'll see the vector fields written in a different form. So a different form. So again, we'll start with R2. So we have in the R2, so this is the xy plane, two-dimensional case. So sometimes you'll see something written like the vector field equals 2i minus x squared j hat. These are called hats. Hat. because it kind of does look like a hat, a very pointy hat. But anyways, so when you see something like this, if you've never seen it before, it might look like, I don't know what these little symbols mean and why do they have hats on. But anyways, what these mean, so the I stands for a standard vector 1, 0, or 1, 0, 0 in the three-dimensional case, and J stands for 0, 1. Okay, so basically, I'll solve through a little bit just to show you what's going on here. But if we replace I with this coordinate and the J with the other coordinate, this is what we're going to get. So when we distribute in, so we get 2, 0 minus 0, x squared, which equals, when you do vector subtraction, then this is going to be 2, negative x squared. So what that means is basically these are just the coefficients of I and J, right? So you can think of it like that, coefficients of I and J hat. Okay, so basically this is your vector field right here. So that would be the same thing as writing vector field equals 2, negative x squared. They just write it like this just because that also means the same thing. So I just wanted to introduce that to you guys so you're familiar with that. And then also let's just do a quick example of a three-dimensional case. So now we have a G, vector field G, equals, let's say they give it to you like this, y times, square root of y times I hat plus 4xz times j hat minus 6y k hat. So in this case, we have to have three variables, I guess, or they're not even variables, they're standard vectors or standard basis vectors. They have a special name, but anyways, so in this case, I equals 1, 0, 0, j hat equals 0, 1, 0, and k hat equals 0, 0, 1. So basically what I is doing, that corresponds to your x-axis. This corresponds to your y-axis. And the last one corresponds to the z-axis. Okay. Alright, so anyways, the way you would write this is, again, just pull out the coefficients, and your x coordinate for your vector field is going to be determined by the square root of y. The y coordinate is going to be 4xz, and your z coordinate is going to be negative negative 6y, sorry. Okay, so then I'll draw a little arrow there. Okay, so that's all it means there. Alright, so now on to a new topic.